Hi, so we're project group number 30, and our project is called Perceptual Guided Mask Latent Refinement for High Resolution Inpainting. In the age of digital media, the ability to seamlessly edit and restore images becomes more important than ever. One of the most challenging tasks in this domain is high resolution image inpainting, which is the task of realistically filling in missing regions in large detailed images. Solving this challenge is vital for applications like restoring old photographs and content creation for media, all of which demand seamless large-scale results. Recent methods have focused on scaling these ideas to higher resolutions. The large mask inpainting model proposed by Suvorov et al. Is a key benchmark for such high-resolution image tasks. Yu et al. Proposed a new method of clicking and filling named as Inpaint Anything, which combines the Segment Anything model for automatic mask generation, Llama for structural filling, and Stable Diffusion for texture-driven content, thereby extending inpainting to interactive editing. More central to our project, Polstresta et al. Proposed a course-defined iterative refinement technique to improve Llama's inpainting result. Their method optimizes feature masks using a multi-scale loss to enhance global consistency. And our research question is, how can latent space optimization be made stable, localized, and effective for improving image inpainting model outputs across different resolutions?
So in terms of dataset, we use the Unsplash Lite dataset that has 25,000 of nature-themed high-resolution photos. And for masks, we use brush strokes with different thickness. If you look at the image in the middle column, we have medium, big, and thin brush strokes, and then we're going to evaluate our models on those separately. Then in terms of baseline model, it has the refinement method added to the Llama model, which is basically an encoder-decoder network that takes in the image as input and then downscale it into the latent features, which are lower dimensional, and then it's fed into the decoder, passed through convolution layers, and then make the prediction. And then the feature refinement comes in after we make the prediction. We back propagate into the feature representation and then refine it separately for several iterations and then make the final prediction. So in terms of loss, we used the L1 loss. So the first part, we compare the prediction on the background area that's not masked of our prediction and our original image. And the second part, we compare the masked area of our current prediction and the previous predictions. So in this way, we keep the high resolution refinement consistent while leaving valley regions unchanged.
Our proposed method also run fully at inference time by refining the latent feature instead of updating model weights. We added two components, the perception loss and the mask latent module. We compare VGG feature between the current prediction and the upsampled previous scale output. This encourages consistent texture across scales and improved details. Our final loss is the sum of the baseline multiscale loss and our perception loss, and this keeps the core structure while adding high-resolution texture improvement. Then we apply the downsampled mask to latent gradient so that only mask-related latent features are updated, preventing changes to other areas. Our pipeline builds the image pyramid and runs the model once at the closest scale and refine latent feature at higher scales for T iterations, and all model weights stay frozen to make this an easy plug-and-play refinement module.
We use the following four metrics for evaluation. Among these metrics, LPIPS and FIG were used in the original paper. So without getting too much into the details, LPIPS is essentially perceptual similarity. FID measures the distance in distribution between projected and real images. PSNR focuses on the pixel level accuracy, while SSIM measures structural similarity. So here are the results. In this chart, we see the performances with respect to LPIPS and FIG. Our proposed refinement model performs better than baseline refinements in LPIPS on medium brush and thick brush masks. We also use PSNR and SSIM to evaluate the performance of our model. Our model with only perceptual loss performed the best on both metrics in thick brush and PSNR in medium brush. Our model with both R1 and R2 performed the best on both metrics in thin brush and SSIM in medium brush. Here's a visual of our results. The first column is the mask image, second column is the original image, and the rest are results produced by different models. Finally, here are some strengths, weaknesses, and limitations. We believe that perceptual loss improves visual consistency, mask latent refinement helps improve local details integration, but additional complexity is introduced in the model. There's latent refinement, which leads to overfitting, and some limitations include, because the thing is based on big llama model, it would inherit all its biases, and since we're not seeing big improvements, we may be reaching computational limits of the big llama model. Thank you for listening.